This is a short video about phenol, its structure and some of its reactivity. So the structure of phenol is very similar to benzene, as it's just a benzene ring, which I'll demonstrate by the Kekulé structure, with an OH group attached. If you don't know the structure of benzene, I recommend looking at my video about the structure of benzene, as it will help with the structure of phenol. So what you have here, similar to benzene, is your delocalized pi system, because you've got p orbitals on every single carbon of the benzene aromatic ring, and as you remember, they all overlap together, and I'll just show the overlap on the top, and they overlap at the bottom as well, and that gives your delocalized pi ring of electron density. But what actually happens in phenol is, because you have a p orbital on oxygen as well, that can actually overlap into the ring of delocalized electrons as well, partially delocalizing. So not fully, not like these ones, not all the electron density is shared, it's only partially delocalized, so it increases electron density a little bit. And that's the structure of phenol. That's how it differs from benzene. Now what is the result of this? Well, because the p orbital from oxygen donates electron density, the aromatic ring in the center actually has more electron density than its benzene counterpart. This means when molecules, diatomic molecules such as bromine, come close, they can be polarized. So if you remember in alkenes, as they come close to a double bond, they can actually polarize them if you had the carbon-carbon double bond here, as the electron density of carbon-carbon double bond pushes the shared pair of electrons kind of towards the other one, causing a partial charge, meaning that it can attack and so forth. Well, the same kind of thing can actually happen with phenol, because it now has a high enough electron density. Unlike benzene, benzene's electron density was not quite high enough, which makes it more reactive. But there is one key point before we talk about the reactions that we have to remember, and that's phenol, the OH group, is electron donating, similar to an NH2 group, and that is something called ortho and para directing, which basically means that carbon 2 and carbon 4 are the places that they're most likely to be substituted. So we just quickly look at phenol, OH. If you remember that that's carbon 1, that's carbon 2, 3, 4, 5, and 6. So carbon 2 is also known as the ortho, carbon 3 is known as the meta position, and carbon 4 is known as the para position. And basically, an electron donating group such as an OH or an NH2 group is ortho and para directing, or carbon 2 and carbon 4 directing, meaning that they're most likely going to be on this carbon and this carbon. And because the molecule because the molecule is symmetrical, it can also appear on here, because carbon 2 is the same as carbon 6. We could just label it the other way around, so we could say that's carbon 1, 2, 3, 4, 5, 6. It's exactly the same because it's symmetrical. So 2, 4, and I guess you could say and 6 directing. Just have to remember that when we're talking about the reactions next. But first of all, we'll talk about its acidity. Because we've got this OH group on the end, and because the electron density, let's just say that's benzene, this is a benzene ring, I won't draw it all out, this can actually dissociate in water and go to the benzene, O minus, and an H plus in water. And because of that, it makes it weakly acidic. It's not fully acidic. It's nothing like a strong acid such as hydrogen chloride, where it will fully dissociate and attack things with protons all day long. But it's enough that it can react with NaOH. So we have phenol can react with NaOH, which neutralizes it to form the salt of the phenol, O minus, Na plus, and H2O, which is brilliant. That's the reaction of neutralization. Because of this OH group that we were just talking about, it can also partially dissolve in water. It's not the best at dissolving because of the big bulky benzene ring. Actually has weak van der Waals forces compared to things like ethanol, which has mainly hydrogen bonding. It dissolves in water, but not very well, and you get a couple of different layers formed. Let's now talk about its reactivity with Br2. If you remember benzene from my previous video, if you would like to react it with Br2, you need a catalyst such as FBr3, and it substitutes a hydrogen in place of it. Bromine goes on, and you get HBr kicked out of the reaction. But when you look at phenol, because of the high electron density, going back to sort of one of the original slides in the video, the high electron density from the p orbital partially delocalizing into this ring, we can actually react it with 3 lots of Br2, and it does not require catalyst. No catalyst, because of the high electron density, and we get a molecule, and I'm going to draw it a bit bigger so it's easier to see, where you've got your OH group still on there. So we've got your aromatic ring. However, because we were talking about its electron donating, it's ortho and para, or 2, 4 and 6 directing, we get this molecule produced, and 3 lots of HBr. So it substitutes in 3 times and requires no catalyst, all because of this increase in electron density from the phenol functional group of OH. That's nice and simple. So that's it for this video, all about the structure of phenol and some of its reactions that may be helpful throughout whatever course you are studying. Please share this with your friends if they are struggling with the topic or would like a reminder through revision. Please like and subscribe for more videos, and let me know if there's any videos I haven't covered and you would like me to cover. Thank you.